Welcome back to Fun with Physics. In class, we've started playing around with electric circuits. And what we've learned so far is that there's something in the wires called charge, electric charge, that we can make move around. And we know that the electric charge is moving because we can get light bulbs to light or compasses to deflect. Now what we want to talk about is the rate of flow of those charges, which we're going to call electric current. So first of all, some definitions. The flow rate of electric charge is called electric current. So when we say there's a current in the wire, what we're actually saying is that there are electric charges moving in the wire. Now, one major confusion at this point is that people confuse a high flow rate or a high current with how fast the charges are moving. And I want to show you that flow rate of charge or electric current is not about how fast the charges are moving. So to see how this could be, that high flow rate doesn't mean going fast, let's talk about water, and let's talk about water flow rate. Now, water flow rate would be the volume of water going by. So it would be measured in cubic meters per second. So it's like a volume of how much water is going by per time. So we're concerned with amount of water going by per a certain amount of time. So if I look up top here at the Mississippi River, the water at this point at St. Louis, you can see the arch right there, this water is going slow, very slow. Down here we have a stream of water, and you can tell by looking at all the white caps on it that this water is going fast. So I might think that the stream has a high flow rate and the Mississippi has a low flow rate, but I would be very wrong about that. Because when it comes to the amount of water going by per second, even if the Mississippi River travels slowly, a huge amount of water is going past some point on the shore every second. Not because the water is going fast, but because of how much water is going by. Likewise, even though the water in the stream is going fast, the volume flow rate of the stream is very low. Because even though the water's moving fast, there's just not very much of it going by some point on the shore every second. So current, which is the flow rate of charge, is not about how fast charges are moving, it's about how much charge is moving. A high current means a lot of charges are going by some point in the wire every second. A low current means very few charges are going by some point in the wire. So make sure to keep flow rate of charge and speed of the charges separate. High flow rate does not mean high speed. So let's talk about how electric current or charge flow rate is measured. First of all, the formula for it, and this is it right here on from the reference tables, is that the current, which is represented by a capital I, is equal to how much charge, which is written as delta Q, divided by time. So Q is how much charge, and T is the amount of time. So we say that current is the rate that charge is moving past a point per second. The units of electric current are amperes, which we abbreviate as amps, which is a very familiar electrical term. People are aware of there are a certain number of amps in a wire. Well, what does that mean? Definition of an amp. When 1 coulomb of charge, which would go in there, moves past a point in a circuit in 1 second, so we put 1 second in there, we'd say that there is a current of 1 amp, or 1 ampere. So 1 amp is what you have when there is 1 coulomb of charge going by every second. Well, to see what 1 amp means, 1 amp current, let's try to do this question. how many electrons are going past a point in a wire that has a current of 1 amp? So I have 1 amp, and I just learned that that equals 1 coulomb of charge per second going by a point in a wire. Well, let me ask this question. Is a coulomb an electron? Well, I know a coulomb is not an electron because a coulomb is a unit of charge. An electron is an object or a particle that's charged. It carries 1 elementary charge. So an electron has a charge of 1.6 times 10 to the negative 19 coulombs. That's a really small amount of coulombs. But right here on the reference tables, it tells me that 1 coulomb of charge, where I have to assemble a whole bunch of these guys to make up a coulomb of charge. In fact, I have to assemble 6.25 times 10 to the 18th elementary charges to make up 1 coulomb. So an electron carries an elementary charge, and you would have to have this many elementary charges to make a coulomb. So if 1 amp equals 1 coulomb per second, then that's going to be 6.25 times 10 to the 18th elementary charges per second. So if I have 1 amp current in a wire, I've got 6.25 times 10 to the 18th electrons going by every second at that point in the wire. Well, if you want to have current in a circuit, what do you have to have? Well, you have to have 2 things. First of all, there has to be a difference in electric potential between 2 points in a conductor or a wire. And the charges are going to go from high potential to low potential. Now this might be easier to understand if I just think roller coasters. So if I take the word current out and I ask the question, what makes roller coaster cars move on a roller coaster? Then we would say, first of all, you have to have a difference in gravitational potential or gravitational potential energy between 2 points on the roller coaster. Masses, or roller coaster cars, move from high potential energy, top of the roller coaster, to low potential energy, bottom of the roller coaster. So I need a difference in electric potential. Just like in a roller coaster, I need a difference in height. If I have a 400-foot roller coaster, but it stays at 400 feet, the roller coaster car is not going to move fast at all. It's when you go downhill, when your height changes, that you have roller coaster cars moving. And then the other thing that you need to make current in a circuit is a path, complete conducting path. And that's really what we call a circuit. Okay, let's just ask a couple final questions before we finish off here. And let's actually start with this second question. Why is the 250,000 volts of the Van de Graaff generator safe, but the 120 volts of the wall socket is potentially fatal? Now, to answer that, let's actually start by considering the first question, which is, what's the difference between getting a shock from a Van de Graaff generator, or lightning, let's say, and what happens in a circuit, like with a light bulb? Well, the biggest difference between the two is that when you get a shock, that is a very brief discharge of electric charges going from one place to the other, and that lasts a very brief time because it is just a finite amount of charge, and it doesn't take very long for it to get from one place to the other. Now, in a circuit, like in your house, there is a steady, continuous stream of charges that are constantly moving from one place to the other, so you're never running out of charges like you would when a Van de Graaff generator shocks you. Okay, so how do I apply this then to the second question? 250,000 volts of the Van de Graaff, that seems like a very high voltage. 120 volts of the wall socket seems to be very minimal. So I would think 250,000 volts is far more dangerous than 120 volts. This is even more true when I consider that 250,000 volts I should think of like a mountain for charges. 200 volts are similar to height for masses. Volts for charges, height for masses. So this is an extremely high mountain for a charge. It means there's a lot of potential energy available. 120 volts is like a small hill. So why would the high hill not be really dangerous and the low hill be safe? And the answer is because although there's tremendous amount of energy available to move charges, there's not very much charge to move, just like we said in this first question here. That once there is a spark, that ends the charge distribution. So the charges are moved by a tremendous amount of energy, but not very many charges. 120 volts is not very much energy, relatively speaking, to move charges, but the number of charges that 120 volts could move is basically how many charges do I think there are in the wiring in my house, or in the wiring in my neighborhood, or in the wiring connected to national grid. Tremendous volume of charges able to be moved. Therefore, that charges moving through my body is what's dangerous. 250,000 volts would be a lot of energy to move charges, but there's just not very many charges to move. So it's generally safe. Now, as a final illustration of this idea of the Van de Graaff being safe at 250,000 volts, but the wall socket being possibly fatal at 120 volts, let's remember that it's charges actually going through me that could cause damage. And let's consider these two situations with water. The tallest waterfall in the world is Angel Falls, 3,200 feet tall. Far taller than Niagara Falls. Niagara Falls is only 180 feet tall. But yet a lot of people want to come to Niagara Falls to see it, but they're not coming to see one of the tallest waterfalls in the world. They're coming because of the volume of water that goes over the falls. Now, Angel Falls is super unbelievably tall, 3,200 feet tall. But notice there's not very much water going over it. So if I think of the height of the waterfalls as electric potential, like voltage. So the height is like how many volts this hill is. And notice that Angel Falls, very high voltage. Niagara Falls, not so much. However, Angel Falls doesn't have much water going over it. Now, water going over the falls would be like current. So voltage would be like how high the waterfall is. Current would be like how much water is going over the waterfall. So Angel Falls, I have very high voltage, but not much current. So I could actually possibly even stand under it, even though it's a super tall waterfall. Even though there's a lot of energy, there's not much water moving over it. Niagara Falls is like a low voltage, but high current device. So Niagara Falls, not as much energy available to make water fall, but a lot of water to fall. So I'm going to say that Angel Falls is like the Van de Graaff generator. Very high voltage, but very low current. Lots of energy available to move water, not much water there to move. For the Van de Graaff, lots of voltage available to move charges, lots of energy, not many charges to move. And Niagara Falls is like my wall socket. Relatively speaking, not as much energy to move charges, but incredible amounts of charge available to be moved. So we would say Angel Falls is a high voltage, low current device, like a Van de Graaff generator, and we'd say Niagara Falls is a low voltage, high current device, which would be like the wall socket. This also can help me understand something that electricians say. They say, it's not the volts, it's the amps that'll kill you. And now I can understand why, because volts are not the actual motion of charges. Volts just tells me how much energy is available to move charges. Amps measures the actual flow of charge. What's going to injure me is electric charge actually passing through my body, and that would be measured in amps. Volts cause amps, and therefore the volts cause charges to move, and it's the moving charges that actually could be damaging to my body.